Hello and welcome back. Today we're talking about curve sketching, which basically means we're bringing together what we know about f prime and f double prime to analyze graphs and equations. Curve sketching is a procedure for analyzing a function and its behavior without the aid of a graphing utility. We can start with what we know about domain, range, intercepts, and asymptotes, and then we can add to that the relationships of f prime, and f double prime over specific intervals to quickly sketch the graph of the function. We'll start with some basic building blocks here. Example 1 says complete the table by sketching the general shape of the curve when each condition is met. Let's start at the top here. If f prime of x is greater than 0, what does that mean about the parent graph? It means it's increasing. If f prime is less than 0, it means the parent graph is decreasing. Let's talk about the double derivative. If the double derivative is positive, the parent graph is concave up. If the double derivative is negative, the parent graph is concave down. Now we'll do a quick sketch. If we have a positive first derivative and a positive second derivative, it's increasing and concave up. If we have a negative first derivative, but a positive second derivative, it's decreasing and concave up. And then positive first derivative, negative second derivative is increasing concave down. And then both derivatives negative would be decreasing concave down. So with those in mind, let's begin. This graph that you see at the right, we're going to analyze it a couple different times from a couple different perspectives. So first, it says y equals f of x on the interval -8 to 8. So this is just the graph of a regular function. On what open intervals is f of x both increasing and concave up? That would be between, -5 and -2, and then between 4 and 6. On what open intervals is f of x both decreasing and concave down? All right, that would be between -1 and 2. At what x values does f of x have inflection points? Remember, inflection points are when the concavity changes. So at -2, it changes from concave up to concave down. At 2, it changes from concave down to concave up. And then at 6, changes from concave up to concave down. All right, changing perspectives. Now, this is the graph of f prime of x. This is the derivative graph. And I always like to write up here in the corner really big so that I'm reminded what graph I'm looking at. And before we just dive into answering questions, let's organize what we know with a picket fence. On the top, we're keeping track of what the derivative graph is doing. And on the bottom, we're keeping track of how does that translate to the parent graph. So first of all, we need to find the critical points or the zeros of the derivative graph. So those would be at -5, and then again at 2 and 6. Now, up until -5, where is this derivative graph? It's above the x-axis, so it's positive. And then between -5 and 2, yeah, still above the x-axis. And then at 2, it dips down below the x-axis, so the derivative is negative there. And then back above the x-axis, so the derivative is positive from 6 to 8. What does that tell us about the parent graph? It means that up until -5, the parent graph is increasing. And then between -5 and 2, well, it's still increasing. Between 2 and 6, it's decreasing. And then from 6 to 8, it's increasing again, which means we're going to have a minimum at 6 and a maximum at 2. With all that in mind, let's go answer our questions. On what intervals is f of x decreasing? Well, we can see that it's decreasing on 2 to 6, where f prime is negative. At what x values does f of x have a local maximum? We can also see that from our little picket fence. We have a maximum at 2 because f prime changes sign from positive to negative. Continuing on in the f prime graph, now we're talking about concavity. So if concavity is involved, so is the second derivative. But how do we get information on the second derivative from the first derivative graph? Well, recall, f double prime is the derivative of f prime. So f double prime is talking about the slope of f prime. So to find our zeros or critical values of f double prime, we need to know when the slope of f prime is 0. So that'll be at -5, and then it goes up, turns around again at -1, and then it goes down, another 0 slope at 4. Now again, f double prime is the slope of f prime. So up until -5, we have a decreasing slope. So that's a negative double prime. And then up until -1, we have a positive slope. So that's a positive f double prime. And then it goes down again until 4, so we're negative, and then up again until 8, so we're positive. Now, how do these negatives and positives translate into our parent graph? Well, if f double prime is negative, that means our parent graph is concave down. If it's positive, it's concave up, then concave down, then concave up again. Now let's finish answering our questions. On what intervals is f of x concave down? Well, we can just look at our picket fence, and we can see from -8 to -5 and -1 to 4. That's where f double prime is negative. At what x values does f of x have an inflection point? Inflection points are where we have a change in concavity. So at -5, at -1, and at 4, because f double prime of x equals 0 and f double prime changes sign either from negative to positive or from positive to negative. Okay, now another perspective. This graph is now the double prime graph. It's the second derivative graph. So once again, let's get our picket fence. And looking at this from the perspective of a double prime, the zeros are just going to be where it touches or crosses the x-axis. So -5, 2, and 6. Now, what's happening to the left of -5? It's above the x-axis, that's positive. From -5 to 2, still above the x-axis, still positive. Then it dips below, so that's negative, and then back above the x-axis, so that's positive. What does that mean for our parent graph? We've got concave up, and then between -5 and 2, still concave up, then concave down, then concave up again. Now let's answer our questions. On what open intervals is f of x concave down? Right here. Whenever f double prime is negative, so that means f is concave down on 2 to 6. At what x values does f have an inflection point? Again, that's where we change concavity. So that would be at 2 and 6. Notice at -5, there's no change in concavity. So that is not an inflection point, even though it's a critical point. This looks scary. Sketch a possible graph of the function g of x that satisfies the following conditions. All right, now we're looking at some G prime conditions, some G double prime conditions, and then some conditions on the graph itself. So let's start by looking at some of our important numbers. We've got negative infinity, -1, 3, -1, 3, go up to 3. So let's just give ourselves some fence posts here to work with. And then we'll start by examining the first derivative. So we are positive in the first derivative from negative infinity to -1 and 3 to infinity. And then we're negative on the first derivative between -1 and 3. So what does that mean for our parent graph? It's increasing until -1, and then there's some sort of a maximum. And then it's decreasing to 3, and there's some sort of a minimum, and then it's increasing again. Now let's check out our double derivative. We are positive from negative infinity to -3, and from -1 to 3. And then we're negative on our double derivative from -3 to -1, and then 3 to infinity. So that's telling us about concavity. We are concave up until -3, and then there's some sort of inflection point. I marked that here. And then concave down until -1. So we have another inflection point. That's interesting. The inflection point is the same as our maximum. I wonder what that'll look like. Okay, then we're concave up until 3, same as our minimum, and then concave down. This might be a little bit tricky to graph, but shall we try it? But before we do, we need to cover just the graph itself. This says the limit as x approaches negative infinity is -4. This is talking about end behavior. That's an asymptote. So we have an asymptote at y equals -4, and then another one at y equals 4. Okay, you ready to do this? Let's connect those dots and see what we get. Woohoo, that's fun. So we're concave up, concave down, and then this is like a little cusp here because it's a maximum and a change in concavity. And then we have another cusp here because it's a minimum and a change in concavity. It's a crazy looking graph, isn't it? Sometimes all we get is an equation. So how do you translate that into a graph? We're going to start from scratch. First, you would determine the domain, intercepts, asymptotes, and symmetry of the graph. 2, you could find critical points and intervals in the first derivative where the function is increasing or decreasing. Determine local maximum and minimum points. Then determine concavity and points of inflection in the second derivative, and then sketch it. We're going to go through that whole process with this graph here. G of x equals x plus 2 times x minus 1 squared. So first of all, we'll find the x and y intercepts. Sometimes it's easier to work with the graph when it's in this form, so I went ahead and expanded it. You can see the x-intercepts sitting right here, so those will be at -2 and 1. You can plug those values back in to find the corresponding y values. And then the y-intercept is when x equals 0, so that's going to give us a 0, 2, because if we plug in zeros for these x's, we're just left with 2. Now we're going to find the first and second derivative. So g prime is 3x squared minus 3. If we want to factor that a little bit, then we can see the critical points of our first derivative, which are -1 and 1. And then the derivative of that, our second derivative, is 6x, and we have a critical point at 0. Part C says complete a sign chart for g prime of x. to find intervals where g of x is increasing or decreasing. Man, we're getting good at these sign charts. So I've got my zeros of the first derivative marked on my little picket fence here. And then I need to pick something below -1 to plug into my first derivative, either there or maybe there. So below -1, I have a positive slope. And then between -1 and 1, I have a negative first derivative or a negative slope. And then above 1, I have a positive. So the graph of g is going up, going down, going up again. Moving on, determine any relative extrema. That's what these are so awesome about. So we have a relative max at -1, and you can plug -1 back into the original function to find the accompanying y value. And we have a relative minimum at 1, 0. Again, plugging 1 into the parent function to find the accompanying y value. Now let's go into the second derivative to find the intervals where g of x is concave up or concave down. My second derivative was 6x. So the 0, anything to the left of that is going to be negative. Anything to the right of that will be positive. So we've got a concave down graph and then a concave up graph. So to identify any points of inflection, a change in concavity happens at 0. And on the graph, that's the point 0, 2. Now I have everything I need to sketch the graph of g of x. So let's start by plotting the x-intercepts and then the y-intercept at 0, 2. Then we have a relative maximum at -1, 4, a relative minimum at 1, 0, but that's already marked there. And then we have a point of inflection at 0, 2. So I'll just put an orange circle around that to keep track of what the heck I'm doing. So let's connect the dots, but just pay special attention to that point of inflection there. We did it. Let's pop some arrows on there and we're done. All right. I understand that this can be confusing. You kind of get your mind in a whirl, going from a derivative graph to a second derivative graph to a parent graph. But again, it's just so cool how it all works out. So I'm glad you were here, and I'll see you next time.